Welcome back, friends. Section 10.3 on geometric series. Today we're going to focus in on being able to determine if something is arithmetic, geometric, or maybe it's something else kind of a series. And we're also going to talk a little about sigma notation and being able to get some geometric functions into sigma notation. So remember arithmetic sequences. Arithmetic sequences have a common difference. What does that mean? Well, if we had 1, most basic 2, 3, 4, 5, so on and so forth, we can get from one term to the next by simply adding 1. So our common difference there was 1. And remember the common difference equation, we had a of n was the first term plus the quantity of n minus 1 times that common difference. In a geometric series, well, there, remember, geometric, we're multiplying, we have a common ratio. And that common ratio was being able to get from one term to the next. So maybe we had 1, 2, 4, 8, 16, so on and so forth. So here we multiply 1 by 2 to get 2, 2 by 2 to get 4, so on and so forth. Or, to get that ratio, we can take the one term divided by the previous term, and it's always the same. So our common ratio there was 2. And our a of n, in case we needed it, again was our first term times that ratio, that common ratio to the n minus 1. So a couple things we're going to ask you to do today. The first is being able to determine, is it arithmetic, is it a geometric, or is it neither? And then can we find the next three terms? Well, example 1, we actually have done example 1 before. And we've talked a little bit about it, but I'm going to throw it at you again, just because I kind of like it. We go 1, 1, 2, 3, 5, 8. And if we look at the common difference, well, we have 0 there, and then 1, and then 1, and then 2, and then 3. So that's a problem, isn't it? So we know that it's not geometric, or it's not arithmetic. Well, is it geometric? Well, 1 divided by 1 is 1. 2 divided by 1 is 2. So I already realized that it's not a geometric either. So what is it? This is actually called a Fibonacci sequence. And in a Fibonacci sequence, we're going to see that we take the first, or the term, plus the term before it, and it gives us our next term. So we could actually put a 0 here if you want it. 0 plus 1 gives you 1. 1 plus 1 gives you 2. 1 plus 2 gives you 3. 2 plus 3 gives you 5. 3 plus 5 gives you 8. So to find the next three terms, I have 5 plus 8. That's going to give me 13. 8 plus 13 is 21. And 13 plus 21 is 34. And it's just one of those sequences that you got to be able to realize and find, hey, I'm adding those two values together. In example 2, here we have a radical, and we haven't messed with a whole lot of radicals. That's why I wanted to show you one. Here we have 2, radical 2, 4, 4, radical 2, and 8. Well, if I add, I can't just add a number. What do I add 2 radical 2 by to get the 4? 4 by to get radical 2 becomes very cumbersome. But if I look at the common ratio, if I multiply by radical 2, 2 radical 2 times radical 2 gives me 2 radical 4. 2 radical 4 simplifies to 4. 4 times radical 2 is 4 radical 2. And if I multiply by 4 radical 2 to radical 2, I get 4 radical 4, and 4 radical 4 reduces to 8. So this we should see as a geometric sequence. So how do I come up with my next three terms? I'm going to multiply by radical 2. So I have 8 radical 2. 8 radical 2 times 2 is going to give me 16. And then 16 times radical 2 gives me 16 radical 2. And those are going to be my next three terms. In example 3, we have 7x, 14x, 21x, and 28x as our terms in our sequence. Well, what can we do to 7x to get the 14x? So on and so forth. Well, if I add 7x, each of my terms, I'm going to end up with the next term. So my 28x, my next term is going to be 35x. My term after that is 42x and then 49x. So this is going to be a linear or arithmetic sequence. All right, in example 4, we're going to get into writing sigma notation using that geometric series. And remember, when we do a sigma notation, we can start our value anywhere we want. I, on the other hand, am going to ask you to start at a specific point on a test or quiz. So we're going to go ahead and set up just as n equals 1, and if we need to vary it, we can vary it later on. So if I look, I have 2, 6, 18, so on and so forth to 486. Well, how do we go ahead and find what our explicit formula is? Remember, our explicit formula for a geometric sequence is a sub 1 times r to the n minus 1. Here my first term is 2. My common ratio, I go 2 to 6 to 18, I'm multiplying by 3 to the n minus 1. Now I got to figure out how high do I come up here. Well, what I need to do then is to figure out what number is going to give me the last term in my series with this explicit formula. So I'm going to take that last term, 486, and set it equal to this explicit formula. I can go ahead and divide by 2. So I have 243 equals 3 to the n minus 1. Well, 243 I know is 3 to the 5th, because I know my Algebra 2 teacher really drilled that into my head, hopefully. So then I know that 5 has to equal n minus 1. Since my bases are the same, my exponents have to be the same. Add my 1, so x, or n, has to equal 6. So my integration, or my summation becomes from 1 to 6 of 2 times the quantity 3 to the n minus 1. I have just one more example for today, and that's if we start our n value as not being 1. So what is that going to look like? Well, again, just like we did in an arithmetic series, I'm going to go ahead and set up a sigma notation with n equal to 1, because n equals 1 is a lot easier to figure out. So I have my first term, which is 4. I go from 4 to 2 to 1, all the way down to, well, this is a 1/8. So I'm decreasing, or I'm taking a common ratio of 1/2. And this is going to be to the n minus 1. I'm not going to really worry about this top number. You can go ahead and figure that out if you want. But it's not going to matter a whole lot, because we're going to change this bottom number. We want to start at when n equals 3. Well, if you remember in arithmetic series in sigma notation, we had to zero out that common difference. And that's really what we're going to do here as well. We want to zero out this exponent. Because if I take this exponent and make it 0, that makes this 1/2 to the 0 being 1. 4 times anything is still 1. So in order to get that first term, we have to make this exponent up here equal to 0. So what is that going to look like? Well, what do I take minus our n value, in this case 3, to make 0? Well, that's 3. And that, hopefully, looks somewhat familiar to us when we were doing arithmetic sigma notation. We changed this number, instead of being 1, to being this number that we started out with. Now we can go ahead and plug in our number. We have 1/8 for our last term to get our upper boundary here. So 1/8 is going to equal 4 times 1/2 to the n minus 3. We can go ahead and solve for n. Solving for n, we can divide that 4 over. So we get 1/32 equals 1/2 to the n minus 3. 1/32, again, great Algebra 2 teacher. So 1/2 to the 5th, or 2 to the 5th is our 32 there. And that's going to equal 1/2 to the n minus 3. So 5 will equal n minus 3. Add your 3 over, we end up with 8 equals n. And that gives us our sigma notation starting at 3. Happy Sigmas!